In this video, we are going to begin our discussion on fractional exponents, the topic of Chapter 4, Section 3. This has 5 objectives. First of all, how do you eliminate square roots? So basically solving problems algebraically. We will also examine distance problems in the plane, specifically parabolas. We will solve problems of the form x to the n equals c, where n is a whole number. We will also solve x to the p equals c, where it's not a whole number, when it's not an integer. And also we will spend some time discussing about reading and writing math and the difference between if and if then and if and only if. Getting started, solve this problem. Looking at the problem, we should always keep in mind our equation solving techniques. Our primary methods for solving are inverse-reverse, the zero product rule, the quadratic formula, as well as guess and check. Let's run through it. Will inverse-reverse work? No. Inverse-reverse requires you to have one occurrence of the variable. And because this one has the x located inside a square root and outside it, inverse-reverse will fail. Can we use the zero product rule? Blob times blob equals 0. All right, even if we subtracted over the x, we should recognize that that's not going to factor anyway, so we can't set up the zero product rule. Does the quadratic formula work? Not right now. And I say not right now because part of our strategy that we're going to learn today is to see how do we change this so that it might fit the zero product, or so that it might fit the quadratic formula. It clearly does not fit now, but with some algebraic manipulation, we can get it there. We're going to see how. Of course, we know that we could graph this using guess and check. We could put it into our calculator, use intersect. We know that is a valid method to get solutions as well. We are focusing on algebraic technique, not the guess and check technique. So, how are we going to get this to fit the quadratic formula? We know the quadratic formula problem pattern is this. And the key characteristic of the quadratic formula, there is no square root. So our primary focus is getting rid of the square root. Emphasizing again, topic number 1, how to eliminate roots. The most important thing, isolate the square root by itself. One side has to have the square root and nothing else. So how are we going to get the square root completely by itself? Alex. You got it, Devin? Because there is the multiply by 2, we will have to divide by 2. Setting it up so that we have the square root completely by itself on the left and blob of stuff on the right. The reason we isolate the square root, how do you get rid of square roots? By squaring, absolutely. So our next step is to square both sides of the equation. By squaring, we know it will cancel out the square root, leaving us with just x plus 3 on the left. And what about on the right? What is x over 2 quantity squared? Okay, x squared over 4. At this stage, I'd like you to think what would you need to do next to make this fit the quadratic formula problem pattern? There are different answers to that question. Dylan mentioned multiply both sides by 4, which would work. If we multiplied by 4, we'd wind up with this. We would then have to distribute across to get 4x plus 12 equals x squared. And then when we subtract pieces over, we could have negative x squared plus 4x plus 12 equals 0. This is one correct way to do it. It is not the only correct way, but it is one of them. All right. Ryan just asked, is that the best way? Best is relative. One other way that we could have done it is to, we could have taken the same first step and having the multiply by 4. But instead of moving the x squared over to the left, we could have multiplied both the other ones to the right. So we would have had 0 equals x squared minus 4x minus 12. Some people would prefer that method. It's also correct, so it doesn't matter. One of the methods that I also considered, we could simply move these pieces over. And have it written here. And that would allow us to simply say it's a fraction. 1/4 x squared minus x minus 3. So all three of these are correct ways to continue. It's just a matter of preference for which way you would like to do. And these aren't even the only correct ways, but there are three of them, and I'm out of room, so let's pick one. Which strategy would you like to continue? Red, blue, or purple? Right? General consensus that students picked was to progress with the blue, so we'll continue now with the blue. How are you going to solve that problem? Yeah, we've got our quadratic formula, and especially we have the quadratic formula program on our calculators. So we can do it by hand, or we can use the calculator. For me, I wouldn't mind saving some time and using the calculator. Let's grab them, plug these things in, and see what we get. Okay, so when we continue, we would say execute our program. And we had A is -1, B was +4, and C was +12. And thus we wind up with our answers -2 and +6. Okay, and we have our two values. Here's a piece that we have to be careful about. These are not correct. We look at it and say, what are you talking about? Because we went through and did this whole part, and we were able to get values. This algebraic technique we did has a flaw. There's a problem with it, and you have to be conscious of it because the calculator won't be. At this stage, when we use the quadratic formula program, we were using this problem. That's a polynomial. Polynomials have a domain of all real numbers. That equation allows every single x value to be possible. That was not our original problem, though. Our original problem was here. And there are domain issues when we work with square roots. In particular, we know that you can't take the square root of any kind of a negative number. And so we know that we can't have anything less than -3 because of the domain. Did we run into any kind of a domain problem there? Do we have an answer that's less than -3? Okay, so we didn't run into domain issues. But you should be careful about that. Sometimes you can wind up with domain problems with problems like this. Okay, Devin asked why we can't have -3 because of the square root. We know because of square roots, we need x to be greater than or equal to 0. Let me rewrite this a different way. If we are going to take the square root of a number for it to be domained, for it to have a domain, it has to be greater than or equal to 0. And so basically we just looked at this part and said x plus 3 has to be greater than or equal to 0. So when we subtract, we need x is greater than or equal to -3 for domain problems. Well, there is also another algebraic problem that we run into as well. If I were to tell you, and I want to put this on a new page so it's less cluttered. True? True? So if I take a square root then, and basically we look at it with kind of the shortcut, squares and square roots cancel each other out, right? Well, if these cancel each other out, those true? The problem that we have to keep in mind, square root refers to the positive square root. This top one is saying, and that's not true. Here's the short version behind what you need to do, because I know this is beginning a little bit long-winded. When you use this squaring technique, you will often create an answer that's true in the altered problem, but it's not true back in the original. And it's because of this problem. What you need to do is determine which one actually works. Which one of these was valid? Maybe it's both. Maybe it's one of them. Maybe it's neither. Let's find out. We will have to plug these back in and find out. So 2, -2 plus 3. Is this true? So -2 plus 3 is 1. 2 times the square root of 1. Square root of 1 is 1. And so this is not true. This doesn't work. And it was because, algebraically, the square root of that 1, with the quadratic formula, it was taking the -1 root instead of the +1 root, and that's what threw it off. Let's check the 6. 2 times 6 plus 3 equals 6. 2 times the square root of 9. So 2 times 3. Yes, that one works. And we actually have this one correct answer. Yes, this is the only correct answer to the original problem. Here's our last example in this video. All right, so looking at this particular problem, first thing I'm thinking about is domain, just because I want to be careful about it. This one requires that x be greater than 0, greater than or equal to. The second square root requires that we have greater than or equal to -5. combining them, when are both of them true? When x is greater than 0. So because of these two things, because we need both of them to be true, that tells us we get x is greater than or equal to 0 for our domain. Immediately, we know, in the end, if we get a negative answer, we can throw it out because it violates domain. Now, of course, we have a difficulty here in that we have two square roots. How do you get rid of them then? There's only one way to get rid of a square root. You got to square it. And so if you're going to get rid of one, you must have the square root completely by itself. So I look at this particular problem, and this is not the only correct way to do it, but I recognize I could rewrite it this way, which will then allow me to square both sides. And when we square both sides, what do we get? Well, we'll have just x plus 5 on the left-hand side. What about on the left? Well, you'll want to keep in mind that with an exponent of 2, we could expand this using the FOIL method. First, 10 minus 10, not 10 minus 10, 10 times 10 gives us 100. And square root of x times square root of x is just the x. Negative times a negative gives us a positive. But don't forget the cross product term. We also have 10 times the negative square root of x. And the second cross product term, negative square root of x times 10. And so we actually wind up with those two pieces as well, based on the expansion. Now we can combine those two things, of course. Negative 10 root of x minus 10 root of x. Together, they combine to become negative 20. Okay? So why go through and do all that? Well, it's better now. Instead of having two square roots, we're down to one square root. So let's isolate this single square root, get it all by itself, and then we can do this squaring process again. So subtract an x over. Subtract 100. And that will give us negative 95 equals negative 20 times the square root of x. And we are fortunate because in this particular one, this isn't a quadratic formula. This one's just inverse reverse. We have a single occurrence of the x. And so we could divide by negative 20. Negative 95 divided by negative 20 equals, right, that's 4.75. And how do you get rid of your square root? By squaring. And so we get our final result, 4.75 squared, which equals, and would you say that again, please? 22 point. and we have a solution. We should be careful though. Is this potentially, wow, is this potentially an extraneous solution? We have to check it. We must put this back in the original to see if it worked. So, square root of x plus the square root of x plus 5 equals 10. So let's check it out. Well, the square root of this part we know is 4.75. And 22 plus 5 would be 27. So the square root of 27.5625 is how much? We got 5.25. Is that true? Yes. So, verified correct. Okay, there seems to be a little bit of a confusion. This part was the square root of 22.5625, which is going to be 4.75. And I knew that right away because we got that number by taking 4.75 squared. So if I then square root it, I go right back to the 4.75 that created it. On the second part, we had 22.5625 plus 5, which gives us 27.5625. And when we use the calculator, the square root of 27.5625 is just 5 1/4. That's where the numbers were coming from. Did that clear up your question, sir? All right, at this point, we'll stop this particular video because 20 minutes is long enough. In future videos, we will continue working on these objectives. We saw today eliminating roots. In next videos, we will focus on distance in the plane and solving.